Hi you guys, today we're going to talk about correlation coefficients and lines of best fit. Okay, so let's start off. A correlation coefficient is represented by the letter R. So a lot of times they'll say R equals instead of saying the word correlation coefficient. And the closer the number is to 1, the closer the correlation coefficient is to 1 or -1, the stronger its correlation. The closer it gets to 0, the weaker. So let me explain to you what this means. If you have data points, like look at this example right here. These data points are really close together. That's pretty strong. It means you can predict much more accurately that the next point is going to be right around here, right? That's all tight and close. So that's a very strong correlation coefficient. And look at the number. R equals 0.99. That's very close to 1. The fact that it's positive tells us it's a positive slope. All right, so that is very close to 1. That's very strong data. It's a high correlation coefficient. This number right here, it's a little tiny bit weaker. You can see these are spread out a little bit more, but it's pretty strong as well. It's a negative 0.9, almost -1. So you know that it's strong correlation coefficient and it has a negative slope. Okay, I guess I should put R in front of all these. All right, you can see now this one's getting a little more spread out. You can still see it's a negative trend going down here, but these points are getting a little bit more spread out. So that's a little bit weaker. And then something like this over here would be much more weaker. It's closer to 0. So negative and positive tells you if the slope is going to be negative or positive, and the closer it is to 1 or -1, the stronger it is, the tighter it is in there, and then as they get weaker and weaker, they start to spread out. So like this one, you really don't know. There isn't much of a trend at all, and sometimes that's really hard to see. All right, so like if on a test I gave you several different ones and maybe I gave you the correlation coefficient and you had to match them, or just tell me maybe if I gave you all the correlation coefficients and I said arrange them in order from the strongest to the weakest. All right, remember negative and positive doesn't determine if it's weak or not, it just determines if the slope is negative or positive. All right. The next thing I want to talk to you about is what's called a residual plot. And what a residual plot does is it helps you determine if you have a good line of fit. Okay? So if I had these data points, and so what I want you to remember about data points is these actual points that are in red, that's actually what happened. So whatever this data represents, these points are the actual answers. So if I went around and said, how tall were you at 2 or whatever this is for, that is actually what happened. And then I draw a line of best fit to go through there to say, okay, this is going to help me predict. All right, so this line of best fit is not what actually happened. It's so that I can predict what's happening. I can kind of see what's going on, finding the trend. Okay, so to do a residual plot, we are going to find the difference between what actually happened and what we predicted happened, and then we're going to plot that on a graph. Okay, right over here, I have residual plot tells if the line of best fit is good. The residuals need to be randomly distributed close to the x and have no pattern. So I'm going to explain to you what that all means in a minute with this plot. So these dots are the actual dots, and this was our predicted line. This is our line of fit, and we're going to draw a residual plot down here based on this data. Okay, so if we look at the first one, so at 1, there is no actual dot there, so I have to move on to 2. At 2, there is actually a dot at 1. Okay. My predicted said it should be at 2. So for this point right here, I have a residual of -1. So at 2, this is going to be our x-axis right here. I'm going to make that a little darker. And this is our y-axis. Okay? So we have a residual of -2. So at 2, a -1. At 2, we have a residual of -1. So at 2, we have a residual of -1. All right, so I've dealt with that dot. Now we have to do this one. So this is still at 2. I have a dot at 3, a point at 3. I said that it should be at 2. My predicted value is 2. And when I subtract that, I get 1. So at 2, I have a residual of 1. Now remember, we're not trying to see if these things are functions or not. So you don't have to go, oh my gosh, it fails the vertical line test. It would, but that's not what we're doing right now. Okay, so now I've dealt with this dot. Let's go on to here. Now this is at 3. I have a point at 4. Now I actually said that my predicted value was at 4. So therefore I have a 0 residual, but I'm going to go ahead and put that down here. Oh, was that at 4? Sorry, that was at 3. Put a dot there. I know, everything's so dark. Okay, so at 4, I have an actual dot at 5. My line looks like as if it should have said 6. So that's a residual of -1. Here I have an actual dot at 8. I thought that it would be at 6. So I have a residual of 2. My last one here, I have a point at 6. And I'm looking at the y numbers here to get when I say 6. I thought it was going to be at 8. And so I have a residual of -2. So now that we look at the residual plot, I mean, you can kind of look at this line and go, gee, that does look like a pretty good line of best fit. But when I look at this residual plot, what I'm looking to see is, are some of the dots above this X line right here and some below? We want them spread out. We don't want to see a pattern. So if we had a residual plot that looked maybe like this, you might say, well, wait a second, this is fine because some dots are below and some dots are above. But no, there's a pattern there. So this would not be a good residual plot. That would show, I mean, that's a good residual plot, but that would show the line of best fit does not work. Okay, so no pattern, and you want them close to the X. See, those are pretty close to the X. Now it does, matter on how spread out you make these. And the residuals need to be random. We want to see random. We do not want to see a pattern. Okay, now sometimes it's really nice when you have it like this, but sometimes you're going to see data like this where they give you a chart and they want you to make a residual plot from that. So I went ahead and on a piece of graph paper right here, I just got my paper ready and I put going by 20s increments here, going by 1s here, or this is actually going by 10s and -10s. Okay, so what have they given us? I can't remember the exact situation for this. But there's years going here, so this is going to be my x-axis years, and this is how many students are enrolled in a course or something. And so at 0 time, there was 832, then 872, sorry, yes. And you can see all of these numbers tell you how much are in each year. Now this is the actual data. This is actually me recording what's going on. The equation for the line of best fit is right here, and I hate it because look, I see a decimal here. These aren't exactly small numbers, and I'm going to make a residual plot based on this information. So remember, this is my actual, this is my predicted. All right, well, what I can do is I can plug in. Well, on this year, on year 0 here, maybe if I made a little chart, that might be a little bit easier. Okay, so now I'm going to ignore this for a second and I'm going to plug in a 0 here. Well, if I plug in a 0 here, I have 877 because 1.44 times 0 is 0, and then I add that. Now what about year 1? I'm ignoring this and I'm making a plot based on this information or a table. All right, so now I'm going to plug in a 1.44 plus 877. And I get 878.4, that's good enough. Put a 2, 1.44 times 2. 879.9. Hopefully I'm getting these numbers right. 3. .3. So I'm just filling these numbers in. Oh, did I do something wrong there? Hold on. Times 5 plus having a hard time fitting it all. Let me just go down here. 6 is going to get me 885.6, and then 7. $887.08. Okay, so basically I've made a data chart of what actually happened, or that was given to me, and then they gave me the line of best fit. And so what I have to do is I have to make a residual plot to see if that line of best fit works. Okay, so here's my residual plot. I take the actual right here and I subtract the predicted, and the line of best fit is my predicted. So I'm going to put 832 minus 877, and I get, maybe I'll make a little chart here, negative 45, right? So at the 0, I'm going to go to negative 45, which is going to be right in here, probably a little bit higher. Okay, then my actual, 872 minus my predicted, which is negative 6.4. My actual minus my predicted, oh, something went wrong there. My actual, oops, minus predicted, $25. So I can either just make a chart real quick and then plot that, which is probably what I'm going to do. It's taking a little bit of time. So at 3, I have 928 minus 881, 46.7. At 4, now I'm wondering if I was paying attention to the negatives. Oops, something's wrong there. Let's do that again for 4. 903. Feel like I keep pressing the decimal maybe. 882.8. Yeah, much better. So 20.2. 5. 2.8, that's really close. And the last one, okay, so now that I have my data, I'm going to try to graph that. And so I showed you the first one. At 0, it was a negative 45. At 1, it was negative 60. Oh, I guess I need to keep going here. Negative 60. Oh, sorry, that's negative 6. Maybe not. So up here, at 2, it's 25. At 3, it's positive 46. At 4, it's 20. Five, it's 2. 6, negative 20. 2. 7. Okay, so now when you see, you can look at that data. And let's go through our questions. Are they randomly distributed? Well, to me, it looks like as if there's, some kind of U. I mean, I know on the ends they're on this side, but in the middle they're all above. So that doesn't seem right. They're not very close to the x-axis. I mean, that's 40 above and that's more than 40 below. So they don't seem like they're close to the x-axis. I don't see a definite pattern except for it might be some kind of U. So maybe there is a pattern there. So I would say that this is not a good example. This line of best fit is not a good line of best fit. And I was able to tell that because of my residual plot. Okay? So I want to just show you a few residual plots that I thought, okay, this will help you just get a good gauge of it. Okay, so if you look at this one here, can you see this? All right, this is a residual plot, and we can look here. Well, look at how far these are apart. That's only 1 and 2, so I know it appears spread out, but it really is not that far. It says the residual plot shows how well a linear model fits the data. The residual plots are randomly distributed on either side of the x-axis, and they cluster close to the x-axis. So they would say that this shows you it is a good line of best fit. And you can see the one that we just did a few minutes ago. This was the original plot, and you can see, yeah, that line really isn't going through it. The data should have it shouldn't be a straight line kind of thing. Okay. The next part I wanted to talk to you about is, find my paper. Sorry. Okay. It's about causation. And causation is just what you think. Is one thing causing the other? And sometimes it's a little bit difficult to tell. The first one says the number of hours of sleep, does that help you get higher test scores? And I would say that's true. We can imply that people who sleep longer do get higher test scores. Temperature outside, compared to the number of people at the beach, yes, the temperature outside could cause people to go to the beach or not go to the beach. The weight of a person causing them to read more. That does not mean your weight cannot, just because, that might happen, it doesn't mean that your weight is causing you to read more or causing you to read less. The number of cars outside, does that cause there to be an increase in population? No. Usually, now if it was the other way around, do the population cause there to be more cars on the street, then that might be yes. Okay, so of course there's some exceptions to these rules, but for causation, you just have to see, does the first one cause the second one to happen? All right, the last thing I wanted to talk to you about was interpolation and extrapolation. And at first I've never taught this before, and then I was like, oh my gosh, what is this now? And when I was looking at it, it's really kind of easy to explain. If we had data, and let's say I was talking about measuring my height. Okay, so I don't record myself every single day, right? I record myself at 1, and then maybe 2, 3, 4, maybe at 5, when I was born at 5, 6, 7, 8, whatever, 9, 10. Okay, let's say I stop here. And then my height, so I have all these data points. Okay, this is maybe 1 foot, 2 feet, 3 feet, 4 feet, 5 feet, 6 feet. Not the best graph, but this is what I'm trying to show you. So if I have data, right? So my parents put a point there, they measure me here, they don't measure me that much, or maybe actually we do a lot when we're little. Okay, am I 3 feet when I'm 5? 1 feet when I'm born? That's not that bad. Okay, I have a little growth spurt, this is what happens, and then I start to get older and not as fun, so maybe they forget to measure me, and then we see that. Okay, so this is just data points, And this is exactly what you think. In means inside. So interpolation just means that if I'm asking you, hey, how tall do you think I was when I was 6? You're using this data to get that information. 6 years old is inside my data set. For extrapolation, it would be if I said, how tall do you think I am at 20? Outside my data set. My data set is between 0 and 10. Now I can draw a line of best fit to predict what I am at 20, and I can also use that line to predict what I am at 6. Interpolation is if I'm doing it inside my data, so 6 years old, and extrapolation is if it's outside my data set. Okay, and it's like out here and it's not within that set. All right? Okay, you guys, sorry such a long video today. Tomorrow it will be shorter, I hope. Okay, see you guys later. Bye.